This conference will now be recorded. Hello,
Well,
nice to see you all.
oh, hello. Hi, Kirsten. Welcome, everybody. My name is Dr. Mary Beth Neely. I'm the scientific coordinator for GEOAquaWatch. And it's my pleasure today to introduce our two speakers for the GEOAquaWatch webinar that we're holding today. We are recording this webinar. It will be posted on our website, and I will provide the link in the chat. It does take me a couple hours to get that posted up on the website after the webinar is completed. And our past webinars are on there as well. You can review at your leisure. I would just remind everybody to please mute your microphones if you're not presenting. We will have an opportunity to ask questions through the chat, and I will moderate those questions at the conclusion of the talks. Or if you, at the conclusion of the talks during the Q&A session, if you would like to ask your question directly, you can unmute that at that time and ask the speakers your question at that time. It's my pleasure today to introduce, we have two speakers. The first speaker will be Dr. Petra Phillipson from Brockmann Geomatics. She holds a PhD in aquatic remote sensing and has served as a remote sensing consultant since 2003. She actually co-founded and is vice manager and consultant at Brockmann Geomatics since 2011. And she has a personal interest and focus on aquatic, national, European, and global assignments and research and development projects. She's also the project manager for BIOMONDO, which she's going to tell us about today. And our second speaker is Dr. Victor Martinez-Vicente. He holds a PhD in marine optics and is currently senior scientist working at Plymouth Marine Laboratory since 2002. His research focus is on developing new algorithms from ocean color remote sensing for scientific and societal applications in the marine environment, such as for marine debris and biodiversity. Victor is the project lead for BOOMS and BiCOME, which he will be speaking about second today. So bear with me just one moment. I'm going to turn off my camera, and the floor is yours, Petra.
Thanks a lot, and welcome everyone. So today me and Victor will present 3 ESA-funded projects called Biodiversity Precursors to you. They are 2-year projects and they will end in the end of this year. So I will talk about BIOMONDO, which are focused on freshwater ecosystems. And then Victor will tell you more about BiCOME for the coastal ecosystems and BOOMS for the open ocean. And these are the nice logos we have for these projects. And as you can see, I've put another 4th logo down here. There is also a precursor focused on the terrestrial ecosystem. It's called EO for diversity. But for today, we will stick to the aquatic environment. So the precursors are the Commission's and ESA's joint initiative to advance Earth system science and its response to global challenges that our ecosystems are facing today. So the main goal is to identify gaps and demonstrate how Earth observation, satellite data in this case, in combination with models and in situ data can contribute to biodiversity modeling. And in the end of our projects, the impact of the results that we have achieved will be assessed from both the scientific and also from a policy point of view. And it should contribute to the development of an agenda, a scientific roadmap for the implementation phase of the ESA and EC flagship action. So these projects are precursors, which means that something more and with a larger scope should follow afterwards. So I will now start with BioMondo. So now we set focus on inland waters, fresh waters. And these are the partners and also the main people involved in BioMondo. It's us from Brockmann Geomatics. We are located in Sweden, and we have our colleagues in Germany, Brockmann Consult. And then we also have PBL, which is the Netherlands Environmental Assessment Agency, and Deltares, also from the Netherlands. And the number 5 here is then EWAC from Switzerland, with focus on aquatic research. So these are the project partners doing the job in our project. This is what we started with, a multi-dimensional challenge cube, which includes the main threats, the different ecosystems by variables, and the different freshwater ecosystems. So pollution, habitat change, climate change, and all the ecosystem services that these different ecosystems can provide. And each of this, what we can call a cell in this cube, is worthy a study of its own. But for BioMondo, we had to make a limited selection with the focus of BioMondo. And we have selected 3 of them, these so-called cells, which we have further developed and which we would like to demonstrate when all the developments are done. And after this slide, we do not call them cells anymore, we call them pilots. And here they are, our 3 pilots for BioMondo. So pilot 1, addressing changes in the trophic status in lakes. And we have the title Eutrophication for this one. Pilot 2, addressing long and short-term changes in water temperature. And finally, pilot 3, addressing effects on biodiversity in rivers from, as you can see in this case, dam constructions. So I will present these pilots in more detail in a minute. So the scope of BioMondo is to identify the main knowledge gaps and challenges in biodiversity monitoring, where Earth observation-based products can contribute, not only by themselves, but as a combination of Earth observation data, biodiversity modeling, and in situ data, and also using machine learning and information and communication technologies. So we will try to create something more on a higher level than just the data itself through this combination. So to develop and demonstrate these pilots, we need data. And we are now actually in the final stages of the data collection task. At least the main parts, as these developments might require some iterations when we see more results. And for this project, we are building a BioMondo data cube, and these are the main components. I hope you can see my little arrow here now. So this is the BioMondo data cube, and in this cube we add data which comes from our own processing. We are not developing new base products in that sense, but we are doing some own processing. We are also adding some standard products. For example, we are using data from the CCI Lakes dataset for our pilots. They are also added here, formatted and added to our cube. We are also including in situ data for validation, for example. And these red ones correspond to different results from partners' models, which I will tell you more about. And as you can see, this arrow goes both ways. So it could either be results from the models that go into the data cube, or the models using Earth observation data, for example, and then delivering a result back. So all these are collected for the different pilots and for the different sites in our data cube. And we have also implemented a viewer and an API for us to demonstrate the results, and also for interested experts to be able to look at the data and access the data themselves. And there are also other possibilities to work on the data if someone would be interested, and that also goes for all of you listening now, of course. So we have collected a lot of data, and we have set up several models and are now developing these 3 pilots. So I will tell you a bit more about our pilots. So pilot 1, which was on eutrophication. There are, of course, many aspects where the benefits of Earth observation data can be demonstrated. And the most given one is to provide EO-based water quality information with its high spatial and temporal resolution that none other technique can provide. But we also want to take a step further, and we have implemented different factors related to phenology and change for these different parameters. So the data itself can be used in many ways just to assess the trophic status, which is listed here on top. And then we also look at the phenology and the change of all these parameters. And the possibility is, of course, to support policy and different measures with data and see the effect of these measures. And finally, we are also testing assimilation of Earth observation data in our partner Deltares model. So I will give you a bit of examples now in the coming 2 slides. The first step for all pilots is to make a quick validation of the base products to gain confidence in its performance. And what you see here is an example for Lake Markermeer and IJsselmeer in the Netherlands, where we have compared Earth observation derived chlorophyll. It's from this CCI Lakes dataset, and with the situ data with good results. And this has been done for all the pilots and for other parameters, so for temperature and turbidity and so on, before we start to further elaborate these products. So, I mean, this is a first step. One can assess the trophic status using the Earth observation data. And then we can start analyzing the data, and we have developed different parameters telling something about phenology. So, for example, we can study blooms, and based on this time series, we can then assess these different parameters. And blooms, for example, then might become more frequent, and they might last longer in an eutrophicated lake. So there are many parameters that we can look at, and I've listed some of them here. So bloom peak, the date of the bloom when it starts, the duration and the amplitude of the bloom. So this we can assess for every year that we analyze, and then we can also look at the different trends in these phenology parameters. So in the bottom here, we have some examples. We are using this CCI Lakes dataset, so going from 2000 to 2020, so over 20 years for our Dutch lakes in this case. And here you will see the peak concentration. So what was the highest concentration during these years for the 2 different lakes? And the other one to the right is then the cyanobacteria indication. So in this case, it's for the whole lake. So we have assessed the whole lake. So of all the observations that we retrieved from the Earth observation data, how many of them have been also flagged for cyanobacteria presence? So we can do time series with the whole lake, or yearly or monthly, or whatever is needed for the different applications. And of course, we can also look at the spatial dimension when we have Earth observation data to see how it varies in Lake Marken and Lake IJssel in this case. And the last point with respect to pilot 1 is that we are now presently working on data assimilation. So we are using Delft 3D, which is Deltares modeling suite, where we can explore hydrodynamics, sediment transport, morphology, and water quality. So it's a 3D model, and we are exploring the possibilities to integrate Earth observation data in the model. And what you see below here is a comparison of, to the left, when in situ temperature from a few stations in that case are used to drive the model, and this is the output chlorophyll for 1 year, so 2020. And this is compared then to how it would look if we instead would use temperature data from Earth observation. And so this is no wrong or no right. This will be the next step to explore this, and if the spatial dimension of the Earth observation data could even give greater benefits than the station data that is available for these lakes. So it's 2 examples, and we are exploring the possibilities, and now we will evaluate what can be done. If I then move on to pilot 2 concerning temperature, we are exploring the impact of changes in water temperature, so long term due to climate change, and also heat waves on freshwater fish diversity. And so as you might know, lake ecosystems are very vulnerable to these temperature changes, directly through the temperature affecting the different species and approaching or exceeding their resilience, and indirectly through effect of the amount of oxygen in the water, and also as we can have an increase of cyanobacteria blooms or algal blooms in general, which also consumes oxygen when decomposing. So accurate data on surface water is crucial for also estimating the impacts on biodiversity. And in this case, we are looking at 3 different lakes, Lake Marken, which I showed you before in the Netherlands, Balaton, and Lake Mälaren, which is not very far from where I'm sitting now. So in this case, we are then exploring the possibility of using lake surface water temperature from Earth observation, together with a recently developed model by PBL, one of our partners. It's a predictive model, and it predicts a heat tolerance. So how much can the fish cope with? And this is species specific and lake specific, and then per date. And what you see to the right here is the different variables that affect this heat tolerance. So for each lake, we are starting with a list of species that can exist in the lake. And in general, Earth observation data can complement or replace in situ data in such modeling events. But we have also added another aspect to this one. So what we are doing is we are using this modeled heat tolerance per day and per species, and then we are subtracting the daily lake surface water temperature data. So we get a difference between what the fish can cope with and what the temperature actually was on that day. And this can be aggregated per day or per month or per year. And the example you see here to the right is when we have aggregated the data over a long time period. And it's better to go per year or per season, but this is just one example to show you what we are up to. And when we do this subtraction, what is generated is something called warming tolerance. I'm not very friends with this concept because it feels like a property, but it's something saying you how far is each species from what it can cope with. So in this case, we can see that the European smelt and Vendens are, with the present temperature that are prevailing during these years, approximately 5 degrees from what it can cope with on the annual mean. But we will now move on further and look at different years, and when we have these heat waves where fish death can occur and so on. So this is what we're doing for pilot 2. And for all the pilots, we are trying to validate the results, which is not so easy. Biodiversity data is not very much available. We have something for Lake Mälaren, which is close to where I'm sitting, where the Swedish authorities has made hydroacoustic measurements, which can tell us something about the fish densities per species and their geographical distributions. So if we are using our warming tolerance for a specific month, we can also compare it with fish densities and the species and see if we can see any change due to these heat waves that, for example, occurred here in Sweden in 2019, and I think in many European countries. And we will also consult our team and external expert knowledge to see if this makes sense. And then finally, our pilot 3, dealing with connectivity. So in this case, we are looking at the connectivity effect by adding dams to river systems. And we are interested in how it affects the habitat, the fragmentation of the habitat, how it affects the dispersal routes. We are looking at the effects on the water quality, both upstream and downstream. So how it affects the sedimentation and turbidity, which has a large effect on the deltas downstream, which constitutes of huge ecosystem service areas, and also how it changes the habitat extent. So for connectivity, we are working with the greater Mekong region, and EO data could be a very suitable tool to complement the quite inconsistent global information and to assess the multiple and simultaneous effects of these river dams. So we will explore the use of a connectivity index. It's a model published by and produced by Barbarossa in 2020. And it addresses fragmentation, and we will try to identify different species, the groups that are most at risk, and different hotspots areas where the fragmentation is sort of coming to a maximum bad situation, let's say. And we will also, in combination, then look at the water quality and how it's changed when the dams are introduced. And for this data, we're using our own processing of Sentinel-2 data, as it's quite narrow branches and narrow rivers. And this is one example. It is data turbidity. No, this is color data. It's called Phenology. So it describes the color. It's from a point downstream of a dam called Lower Seasun in this Mekong region. It's from 2016 to 2021, and for each month. It was officially opened, this dam, in 2018. So now we have done monthly means and estimated the Fralula index. So it's the color index, how the color is changing. It's getting, so brown is browner and more turbid, and blue is clearer and less turbid. And we can see that when the first turbine began producing electricity was here, and the year after, the pattern changed towards more clear water downstream the dam. And when the dam was officially opened in 2018, we can see that this pattern is even increased and over a longer time period. And of course, both adding the dam and changing the sedimentation and sedimentation transport changes the whole situation, biodiversity situation, and the ecosystem. This is one example how we will work with this data together with this model, this index. So what you see on the top left here is the connectivity index. So going from 100%, and then over the years when dams are constructed, it decreases. This figure shows how much megawatts is added to the system. So from 0 and then up to 2010 or something, how it's increased. And this is a combination of the two informations. And we can then see how the connectivity is changed and how much megawatts is added to the system. And this means that we can check for where is the best placement of dams, what dams would actually be needed to be removed to have a good effect on the biodiversity, on the ecosystems. So we can see that a drastic change here when one dam was added, not such a drastic change in connectivity when these 5 were added. So there are better and worse places in the system to add these dams. And then we can also address the effects in the water quality downstream of these dams. So these are the pilots and what we want to demonstrate. And now we have to ask ourselves, are these good results? Are they useful? And we have the team, and we have also a number of biodiversity experts, and we have our friends in BiCOME and BOOMS, which we can consult and see if what we have developed is of use. So these are sort of the next steps. We will finalize this pilot now, and then we have starting now and in the next couple of months, scientific and policy consultations, where we evaluate the value of these the solutions, the results that we are proposing, and how this new information also can support policy and different support systems. So we start from the pilots, we demonstrate, we try to validate if there is data, we try to assess the science and policy utility and impact together with biodiversity and policy experts. And also for policy, we will generate some showcases which address specific biodiversity policy goals and try to present them in close connection to these goals and how this data could support them. So if you would like to be consulted, if you think you can help us with this, you are most welcome to contact me. And yes, thank you. This is what I wanted to present from BioMondo for now, and I will give the word to Victor. Take you to the sea.
Thank you, Petra. Well, I am setting up Victor to be our presenter. I wondered, could you advise us, do you plan to make that, to make BioMondo publicly available in the future? You know, like public access, open access?
Yeah, I think it depends what's happened. I mean, anyone who would like to explore these results are welcome to contact us and can have a look in the viewer and we can demonstrate. If it in the end turns out to be some kind of tool, it's not known, or if it's if we're on the roadmap said that it needs to be further developed and put in a larger context, we don't know that yet.
Great, thank you. And I just want to let you know, Victor, we are able to see your screen. You'll just need to go into presenter mode. Great, thank you.
Thanks.
Okay. Hello, everyone. It is a pity that in this presenter mode I cannot see all your faces, but I hope you'll be interested about what Petra has just presented. This very nice introduction to our topic of trying to detect biodiversity or proxies for biodiversity from remote sensing. And as she was saying, it is part of an initial effort of the European Space Agency to see what is feasible and what is not from remote sensing. We've had in the past problems with over-promising from remote sensing, and we really want to make this one right from the beginning. So trying to assess objectively that there is a value on the products that we develop. So what I'm going to present today is a little bit of the status of our two years projects after the first year approximately of work. As Petra was saying, this is part of the larger effort. I am not a PML. I represent PML, Plymouth Marine Laboratory, in this work, but this work we haven't been able to do it on our own. We have some collaborators, different teams for the two different projects that we coordinate. And they bring in some very different expertise to the table. So as a starting point, I just wanted to go back on why we are doing this, why it is important, and from the scientific point of view, and also from the, for me, it's from the personal point of view. I think I'm very concerned of what are the impacts that we are causing on the marine environment. We have already maps of potential impacts from human activities and climate activities on the marine and coastal environments. These have been combined from different pressures, but also specifically related to climate change. and we can see that for a variety of species, we can see that there are a lot of impacts at the global scale, predicted mostly from models, but they always the models in the similar way that climate change models need validation. Models that predict risk on the ecosystems, species, distributions, and so on need some sort of verification or validation. And I think the current observing system that we have has a sparse coverage in terms of diversity from point measurements. It's also a problem that the data, the records are take a very long time to go into global databases, and that they take a lot of effort to standardize, and of course they are very, very costly. So any effort in the direction of collecting standardized data sets of global coverage and of long term, it's really, really valuable for this community. One of the aspects that is of most importance is emerging in the literature is the fact that yes, there are many pressures in the marine ecosystem, marine and coastal ecosystems, and some of them come from human activity, and the biggest of all is extraction of resources. So fishing in particular is really strong, but climate change is really affecting in combination with these other pressures is affecting and is becoming the biggest of them all. And this is just a recent study on the effects of the different drivers for only for one aspect of biodiversity, which is the red listed species for protection. And you can see how even though the climate related pressures are not the ones that cause the most effects on the sensitive or at risk species, they are really one of the biggest, and the authors recognize that they are enhancing whatever we will doing, and will be greater with time. So they that is from part of my personal interest, and also from the part of science. We need to provide this data for science, but also in terms of policy, there is a system of environmental and economic accounting that needs at their base essential data on extent of the ecosystems and condition of the ecosystems. So where we are at the moment, it's trying to feed into our data into this ecosystem extent and ecosystem condition information, and so that they can be taken forward into other parts of this larger scheme of environmental accounting. And obviously helps with valuing nature and doing modifications in policy, or even being more convincing about why we should be do more investment in protection. But how then the satellites can help? Well, for us, we are beginning to see as an important part is that we should be focusing on providing climate quality observations for marine ecosystem health, and that these needs to be standardized and at the global scale for the reasons I was saying before, and that they need to be connected to policy. And one of the aspects that,
ब्लू वाली ले लो स्टोरेज
hello,
बॉक्स है
hello again. Is anyone wanted to ask some question? Or? No. All right. So what I was saying is that there is one of the aspects is to define to this seascapes definition, which is areas of the ocean pelagic or also benthic at different depths, where we can identify units of ecosystems of similar biological conditions. So The way we have envisioned how to connect policy and science and remote sensing to this to into a whole system is by connecting with what it's called essential ocean variables, and within them there is a branch which is essential biology and ecosystems, essential ocean variables related to ecosystems and biology, and these are feeding, or they can be related through the primary observations into essential biodiversity variables, and these will feed on into assessments and accountancy. So in this sort of mental scheme or how or structure, we have looked at some of the essential ocean variables, and we're dealing with three of them in BiCOME, which is the phytoplankton, biomass and diversity, seagrass cover and composition, and macroalgal canopy cover, and other three in mainly in BOOMS, although there is some crossover because we also deal with phytoplankton in BOOMS as a connection between the pelagic and the coastal oceans. And then there are other variables, but we don't deal with them, like mangroves and hard coral, but in some areas of further development. So the seascapes is something that goes across these variables, and the main activity that we are doing in BOOMS, which is the first project I'm talking about today, it's to see how we can define seascapes from remote sensing using novel approaches, and how well these seascapes are able to map ecosystems related to these three or four essential ocean variables. In that context, I need to do a little bit, very short introduction on what has been the history of this definition of pelagic seascapes. We're not the first at all to try this. Biogeography has been going on for a long time in oceanography, and it was obviously Longhurst who did first the large scale mapping of the ocean using primary production, physical attributions as characteristics to separate between water areas, between ocean areas. Then there has been other more automatic methods, including remote sensing, and we have also like most recent developments, including different parameters of temperature, salinity, chlorophyll, bathymetry, and creating maps of habitat or seascapes for different regions of the ocean. One of the things that we are trying to approach in a different way is first the part that it's linking ourselves or our studies with the climate record. So we're looking at using as input for our seascape definition data that are stable and allow us to look at very long-term changes. All of these studies before us are depending on a single satellite. So we're looking at input for the Climate Change Initiative dataset from European Space Agency. And the other thing is to move away from relying on chlorophyll A as a proxy for definition of regions. We do hypothesize that the chlorophyll A as retrieved from satellite is not an indicator of the subjacent diversity of the phytoplankton, and optical characteristics may change with with different phytoplankton diversity there. So we try to move away from chlorophyll and concentrate on reflectants. And what we are doing is looking at different ways of defining the seascape. The first one is based on optical water types, and is what we call the Seascape 1. The second one is by doing a combination of optical water types and fronts defined from sea surface temperature. And the third one is going to be looking at combining the surface information from satellites to bioalgo floats to give us some sort of indication of what's going on in the third beyond what the satellite can see. From Seascape 1, we have already got the version 1 that derived from optical water classes, and we have already monthly maps of seascapes based on the optical water types, and we have will be possibly putting them online. They are already in a viewer, and we can see already variations in different areas of the ocean. But we need to interpret them now through combination with our science cases. And our science cases are mostly one related to phytoplankton diversity. The second one, and it will be looking at the ocean dynamic seascapes in the Southern Ocean. So looking at salp and krill mainly, and how it is mapped on top of the seascapes, how good our seascapes are in defining these, and then looking at the changes of those with time. Then we have effects of marine heat waves on phytoplankton, and then connecting that to indicators of fisheries. And finally, we're going to be looking at how we are able to speed up processes and parameterize the mapping that we have found using machine learning approaches. After that, we're going to be taking some of the things that we have learned in the science cases and applying them to specific impact case studies. One is going to be comparing our seascapes with what ecosystem models state of the art can produce. The other one is looking at the Atlantic fisheries and human impacts. And the final one is looking at the effects on predators, on top predators. So now going closer to coast, we have we there have another three scientific cases. Here because the observation requirements are very different, especially for intertidal and subtidal. We have look at this in a with different approach. And the pelagic, we're looking at trying to use it as a connection between the open ocean and the coastal and coastal waters. So for the intertidal seagrass, we've been looking at using implementing scalable algorithms to define, in particular, the seagrass, and our partners are testing, are already using this, and we have already a publication looking at the effects of seagrass coverage in European areas are related to herbivorous birds and their migration. But we'll be looking at the changes of the seagrass trajectory in the northern and southern Europe, not only with our large scale baseline algorithm, but also improving with high resolution in situ measurements from drones. These were some images from that paper there. For the subtidal, we're looking at seagrasses in the Bazaruto in Mozambique coastal areas and Indonesia, and we are implementing a baseline algorithm also that will be scalable, based mostly on Sentinel-2, and we are also testing an improved atmospheric correction algorithm to retrieve potentially different or a better way of mapping the seagrass at the bottom. The investigation here will be looking at the changes of once we get the seagrass maps. We'll be looking at the changes with time and hopefully attributing the changes to changes in turbidity and coastal runoff. For the pelagic phytoplankton, we have already we're using a large scale data set to validate chemotaxonomic approach for diversity and see if we can match those to the seascapes that we have defined. And from there on, then we have to see, in particular, focusing on diatom abundance, see how the diatom abundance change and whether we can map it to some drivers like marine heat waves or other drivers at the coastal scale. And finally, we have got floating vegetation, which we're looking at in the Vembener Lake in India. And with that we've implemented again a baseline algorithm, and we're trying to improve it to produce a measure of change with time in the area where it is a big problem. And also we're going to try to see if we can correlate it with storm events and river runoffs and see what are the impacts of those on the seagrass, on the floating vegetation coverage. For us, our next steps will be to try to increase the community coordination and the community engagement on using Earth observation for diversity assessment. We like to be testing the ecological significance of the seascapes. Because they are at the moment based on optical water types, and of course one could say, okay, but how do they relate to biogeographical regions defined some other way, or what is their importance? So this is what we're actually looking on with our science cases. Then we are really looking into extending the pelagic seascape to be able to link with the mesopelagic. We're working with other European projects to see how we can either connect or compare their biogeographies with ours and see whether there is some maps of mesopelagic regions based normally on acoustics with what happens above on the epipelagic area. One important area would be to see the uncertainty in our mapping. That is really challenging because it's not, especially in the seascapes, there is not a right or wrong answer at the moment, because there is no an objective measure of how you divide the ocean. So we need to see how it compares with other existing mapping approaches and see what we can learn from that. And then we're now open to see, given that we have already some preliminary products, it would be nice to see to hear from the people in the audience or other that are interested in testing the products that we have, so we can have more and more people giving us feedback on what can be improved. And there you have my email and the contacts from the projects, and I thank you very much for your time. I don't know if I need to stop sharing or yeah, probably.
Great. Thank you very much. Victor, I have put your chat, I'm sorry, your email in the chat, and I had asked Petra if you could drop yours in there for us as well. We will now take any questions from the audience for either Petra or Victor. You can unmute yourself and ask them directly. If you're struggling to unmute, you can type it in the chat and I will moderate it. Anybody have any questions? I have one. I have one to get us started while people are trying to find their unmute buttons. I wondered. Let me scroll up to see what my question was. Do you think that the new hyperspectral missions coming on board, in the next 3 to 7 years, might be useful for BOOM and BiCOME to again evaluate chlorophyll A and pigments and turbidity in addition to reflectance? I know you said you're getting away from using chlorophyll A, but I wonder if the hyperspectral data might make it more appealing.
Yes, indeed. Yes, we have one of the small activities that we have in the project. It's to test. Unfortunately, we don't have at the moment a matching satellite like for BOOMS in particular, because for the very coastal areas we have Prisma, and yes, I think we're playing with some of the Prisma images. I forgot to mention that. But in particular for BOOMS, we would like to test some of the. I think NASA has some initial data for PACE or simulated data for PACE and see what we can get from those as
Yes.
well. But PACE is just launch either next year or so. So,
Right.
but yes, it would be very nice to have that.
I think they did just push it off again. So, okay. There is a question for you from Kirsten Stelzer for Victor. Is the seagrass mapping you perform for eulittoral or sublittoral habitats?
I don't, Kerstin, I don't know what you mean. I don't know what you mean by eulittoral or sublittoral. We talk in terms of
Like,
subtidal or intertidal.
yes.
Yeah, so dry fallen or submerged.
Yes, we have both. I failed to perhaps make it very explicit, but we have one of the products is for intertidal, so emerged but wet seagrass, and the other one is submerged permanently below the lower tide. So
And
yes,
the
we
atmospheric
do.
correction you're working on, is it for the submerged ones or for both?
For the submerged ones.
Okay,
We're
thank you.
working with high geos on that.
Yeah, it was just I think just the difference in freshwater versus seawater for the words there. No problem. Irene Politi asks, Victor, what other data would you need to be able to identify seascapes as they were originally defined beyond the optical water types?
Hi, Irene. Yes, at the moment we're trying to stay with the optical water types. Yeah, we have only included another variable, which is going to be those derived from fronts from sea surface temperature derived from so fronts derived from sea surface temperature maps. So at the moment we're only using, in addition to optical water types, statistics on front location, front extent, from things from front. So SST.
And follow on, you may have already mentioned it, but Igor asks the method for the defining the optical water types.
The optical water types are defined from the paper from Jackson et al. 2017. So they are at the basis of the OCCCI. I see another question from
Yes,
Cedric. And yes,
right.
indeed, it would be very useful to get up to 50 meters deep or more if, for instance, a LiDAR could do it, but that would be very, very useful.
Terrific. Any other questions? You can either unmute or pop them in the chat. I will mention that since you were looking for partners for your testing your seascapes and the ecological relevance, I mentioned in the chat that I think the folks who identify and manage conservation areas, marine protected areas, might be very, very interested to work with you to sort of do a, you know, pre-policy, post-policy evaluation of whether or not those there were any changes noted in the variety of your parameters. So if you need help getting connected to some of those folks, I know many in the US, but yeah. Okay, we have a
Thanks.
question for Petra from Javier. How did you use Sentinel-2 for calculating the index for connectivity case? That was the last case study that you presented.
Yes, no, it's not based on satellite data. So this is a model not based on Earth observation. So in this case, we're using a combination that together will provide more information on how the connectivity changes and then what the effects are. And then we're using Sentinel-2 data. So not integrated with each other in that case. That was for the fish.
Okay. Thank you. Any other questions for Petra or Victor before we
I
close?
have a small mention to the community who's listening today.
Yes.
It's that it would be very nice. One of my conclusion points was to get the community mobilized around the subject of Earth observation and biodiversity. And if you're interested in that, please contact me because I'd like to put a proposal together to Marine Life to do some sort of sub-project into this UN Decade programs. So I'd like to get some people from the community to see if they are interested in uniting to this. How are you saying it? I never remember the word.
Yeah,
Joining this.
collaborating with you. Yes.
Yes, yes,
So
yes.
I would invite you, Victor, to go ahead and send me two or three sentences that you would like to have in an advertisement to collaborate with
Yeah,
you, and
yeah,
I will share it in our newsletter,
yeah.
which goes out to a much larger audience. And I want to thank everybody who was able to join us today for the two wonderful talks by our presenters. And we do appreciate the fact that we have had a lot of webinars in a very short amount of time. That happens sometimes. So we do appreciate you hanging in there and staying with us. Again, the recording will be posted a little bit later today. One final round of applause for Petra, who has already had to leave. Oh, there she's coming back. And Victor for your talks. So thank
Thank
you
you.
very much. Have
Thank
a
you.
wonderful day, everybody.
Thanks
Cheers.
a lot.
Thanks.
Thanks for listening. Bye.
Yes.
Bye bye.